We have really, at this point, uncovered all of the aspects of the XPI representation space for the X and P basis both. We will now study the Hamiltonian, the angular momentum squared, and the z-squared basis for both central potentials and for the harmonic oscillator, where V is equal to 1/2 kx squared. After we study O3 and angular momentum. It's important to realize that we essentially have done no physics at this point, really just mathematics, with the exception of the dynamical evolution as generated by H, where we really just looked at a free particle. It is of great importance that the student reflect on this XPI algebra, this Heisenberg algebra, as the origin of the Fourier transform and as the origin of forms, that is linear operators, that are made from both x and I partial with respect to x. The I here has the purpose of making this a Hermitian operator. Really, almost every object that one can find useful can be built from the x and the derivative. And all of the linear operators can be built from these. Therefore, they really live in this one-dimensional XPI LieAlgebra and representation space. The ability to build product representations, such as Lij, which is xipj minus xjpi, and the pi did not appear here. And to close that algebra, allow us to form an entirely new algebra. That is extremely important, as we're able to make then new algebras from this single algebra. This is even richer when we go to multidimensional spaces, so we basically have several dimensions x and several comparable, exactly the same number of dimensions p with a single I, meaning that we have a Heisenberg algebra in n dimensions. We will do that a little bit later. We've discussed almost exclusively the Heisenberg Lie algebra. We're now going to look at the Heisenberg Lie group. The Heisenberg Lie group, the most general element, can be generated by looking at the most general element of the Lie algebra in the following way. If L, the most general element of the algebra, is lambda 1 times x plus lambda 2 times p plus lambda 3 times I, then by definition the Lie group that's associated with that for the Heisenberg Lie group is given by the exponentiation of that most general element. Now, since I commutes with everything, we can bring this term outside of the whole expression to write it as e to the lambda 3, just a phase and neglect the I, times e to the lambda 1x plus lambda 2p. And that's the most general type of transformation we can have under this group. Now we need to do a derivation, and for that we're going to remind the viewer of several things. We recall that p mu times k was k mu times k. So k is the eigenvector of p with eigenvalue k mu. This is in 1, 2, 3, or 4 dimensions. Likewise for x, the vector y is the eigenvalue of x, giving us position eigenstates. P acting upon y gives us minus IH bar partial mu with respect to y. That's a partial with respect to y. And likewise, this is a partial with respect to k right here. You recall also that we had the projection of the k space onto the y space as the Fourier transform component, 1 over, if we're in 4 dimensions, 2 pi squared. There's a square root of 2 pi associated with each dimension. And here we're assuming that this is a dot product, k naught y naught minus k1 y1 and so forth. And we had the completeness relation written in this form in both position and momentum space. We're now going to consider a translation in the space. We're going to take an eigenvector of position y and transform it using e to the I over h bar with some epsilon mu p mu, where epsilon mu is an infinitesimal vector. and we're going to let that act upon this eigenstate of x. Well, if we let x act upon this to see what kind of eigenvector this whole term is, then we get the following. We can expand the exponential and throw away all the terms that are higher than the first power in epsilon because they're higher order epsilon. Here we can see that we have thrown away an epsilon squared, epsilon cubed, and so forth in that expansion. As x acts upon 1 and y, we get, of course, y nu times y. And the other term, we get x nu p mu, the x nu and the p mu right here with the constants coming out front. But we know the commutator between p and x, and we can rewrite that term as x nu p mu as p mu x nu minus I h bar g mu nu. So we make the substitution of this term in right here, because what we want to do is get the x on the other side of the p where the x can act upon the y and give us a result that we can use. So when we do that, we end up with the following term. Remember, on the left we had x nu acting upon this whole state. We want to see what kind of eigenstate this is. We get y nu plus, and this came from the commutator, we had an x term right here. The x acts upon the y and gives us y nu. P is still an operator. This is just a number. Minus I h bar I over h bar g mu nu epsilon nu. Now, collecting that together, we can see that this is y plus epsilon nu times e to the I over h bar epsilon mu p nu. Now, how did we collect that back together? Well, we did that because this term right here is 1 plus epsilon to that order, and so we can add in a term of order epsilon squared without affecting anything. The easiest way to see that this is equal to this is to turn around and take this and write it as 1 plus this epsilon term, and when this term multiplies this one of those terms is epsilon squared and you throw it away. The other three give you exactly the expression above. Now, because of that, we now have that x, when acting upon this state, gives us y nu plus epsilon nu acting upon that state. It follows that this entire state is an eigenstate of x nu with an infinitesimally altered eigenvalue y nu. Now, we can reiterate that infinitesimal transformation again and again and again an infinite number of times, and we will then retrieve the fact that e to the I over h bar a mu p mu, and now this is finite, is going to give us y plus a, which is a translation of the space. So it follows that p mu translates us in the space by a four position a mu. And that'll work in any number of dimensions. We just have to be careful with our normalization here of the 1 over 2 pi squared. Continuing with the Heisenberg group, we see that the Heisenberg group momentum operator translates us in space-time according to this transformation right here. By symmetry between the x and the p, it follows that the x will generate transformations that translate us in the p space. Specifically, we can write g of b is e to the minus, and of course the only difference is a sign, I over h bar b mu x mu, summation convention again, and then say what happens when this group element hits a momentum eigenstate. And the answer to that is you get this definition right here. And finally, by symmetry with what we had just arrived, this will change k into k plus b. So now, although this is not a symmetry group, it's still very important. It's a type of spectrum generating algebra that transforms one state into another state, not that's invariant under the Hamiltonian, but that it is a physically admissible state with different energy and momentum. There are other algebras and associated groups that can transform, say, a hydrogen atom among admissible states of different energy and even different angular momentum. one can see that it would be very important that if one could start with one state, one particular eigenstate of a system for a complete set of commuting operators, that one have raising and lowering operators that take one to every other possible state. That is exactly what we have here. We can go among all the different possible states of the system, even though some of those may not follow from an argument on conservation of energy, because we're taking our state to a different energy and to a different momenta with this operator here. Finally, we have this transformation e to the lambda 1, and all this operator does is change the phase of a state. Thus we conclude at this point with our work with the Heisenberg-Lie algebra and the Heisenberg-Lie group to realize that this algebra, which is a nilpotent algebra, consists of three elements: x, p, and I commutes with both x and p. Everything is symmetric between x, the position, and p, the momenta, except for a sign. So if we change equations from one to where we were using x, we change them over to p just by changing the signs of the system. And we have now found that x does an infinitesimal translation in the p space, and p does an infinitesimal translation in the x space. This also lets us know that the eigenvalue spectra of both operators is continuous over the reals, and therefore every real number for position and every real number for momenta is allowable. In 4 dimensions, these operators translate us through 4-dimensional space-time, either through all the possible momenta and energy that are available or that of space and time itself. On the one hand, we can think about position space as the space that we learned about with all of our senses from the time we were born. We visualize things in space and time. Other spaces we really don't understand that well. We have no direct intuition about how the world is laid out in momentum space or in other spaces. So it's always important that we take these other spaces and project them back onto our position space to see what these probability distributions or the shapes or the behaviors of things in time are from that point of reference. In particular, we next want to look at the harmonic oscillator, Lie algebra. This is an algebra that actually can be extended from the Heisenberg-Lie algebra by adding a new type of element. It is very important that you understand how we start here in this problem with the Heisenberg-Lie algebra and now end up with an algebra that is larger by one new element. Furthermore, you will see that the Heisenberg-Lie algebra allows us to generate this bigger algebra, much like we referred to a while ago with the angular momentum. The harmonic oscillator algebra that we're about to discuss kind of lives halfway in between position and momentum space and is totally symmetric between the two. Now, we've already extensively covered the harmonic oscillator in classical mechanics, and now we're going to cover it in the quantum mechanical case. The Hamiltonian for our system is, and I'm writing here a script h, is equal to p squared over 2m plus 1/2 kx squared. Now this gives us the kinetic energy plus the potential energy of a spring. And of course, as we have written it here, there are no dampening forces and there is no friction. We can rewrite this with the term omega, where omega is the square root of k over m, in the following way, and where xp is equal to IH bar. You notice that we don't have an ordering problem when we go to the quantum mechanical case, because position and momenta do not occur in the same expression. So this is simply p squared over 2m and kx squared, or we should say m omega squared x squared over 2. We want to eliminate some of these constants and hide them to end up with a more symmetrical problem that will be easier to work with. This way we just don't have to drag as many constants around. So we're going to, with this definition of omega right here, and omega appearing right here in the Hamiltonian, we're going to rewrite script h as a regular capital H times h bar omega. And that's going to give us script h is equal to this expression right here. We are going to define x as being equal to the square root of h bar over m omega times a capital Q, and p as m h bar omega square root times a capital P. With that definition, one can show that the script h now takes the form h bar omega over 2 p squared plus q squared, therefore giving us immediately the fact that the regular h is equal to 1/2 p squared plus q squared. Now if you check the commutation rules, it's very easy to do a substitution to find the commutation rules of q and p. And when we plug those in, we see that we get commutator of q with p is of course this factor times this factor, which just comes out front, times the commutator of x and p. I've written here, of course, the inverses of those terms, which is 1 over h bar, IH bar, which just gives us a commutator of I. So we have also succeeded in getting rid of the h bar in our equation, so that looks a little bit simpler. Now because we know that the commutator of QP is equal to I and h bar is equal to 1, we can take all of the previous equations that we did for momentum and position acting on the eigenstates of position and momentum and take them forward immediately exactly in the same form with no h bar. Therefore, P acting backward on a Q position state is minus I partial with respect to Q times Q. Likewise, H acting on some energy eigenstate becomes some energy times that energy eigenstate again. We can now write, because of this, we can sandwich in a Q with an H and a U to get the following type of equation. By putting a Q on this side and letting H act backwards, we get a minus I partial with respect to Q quantity squared, which makes this positive. This makes it negative again right here. Second partial with respect to Q squared. Remember, the Hamiltonian has a factor of 1/2. We're looking at capital H without the script, so we do not have the h bar omega. And this equation right here will then give us where Q is projected onto U, which gives us U of Q. This equation is the Schrödinger equation. And to emphasize the power of this Lie algebra, rather than solve this differential equation directly, we're going to use some methods in Lie algebra. These methods were originally due to Dirac and the associated derivation. They can be found in Dirac's book and also in Messiah's book, as well as several others. Continuing with the harmonic oscillator Lie algebra. As we work through the algebraic approach, we want to keep the following things in mind. First of all, we began with 3 elements of the Heisenberg algebra, Q, P, and I. We will now define a 4th element, capital H, without the script, called the Hamiltonian. This is an overview of what we're about to do. Now we will, from these 4 operators, find a new basis for the algebra, Q, P, I, and H, which consists of, in this Lie algebra space, an A dagger, an I, and an N. We will look now for, after that, for a basis where N is diagonal, along with capital I, forming the Cartesian subalgebra, which is the only element that will commute at the same time is N. No other function of the A and the A dagger will also commute. The capital I plays the role of the Casimir operator and commutes with everything as before. The A and the A dagger behave like the E plus and E minus operators that raise and lower the eigenvalues of n. And we have discussed those, the roles of the E plus and E minus operators in the Cartan decomposition back when we discussed Lie algebras. Now, these actions are then going to be used to find the spectrum of n. This general procedure right here of where we separate out, find the Casimir operators or the Casimir-like operators, the Cartan subalgebra, and the raising and lowering operators that then move us around over all possible states is something we will do again and again as we look at different algebras. Finally, the system is recast into the position representation where all of this work is seen as techniques with differential equations rather than techniques with Lie algebras. Again, let me emphasize that we see these equations as differential equations that we have solved in the position space, and the solutions to that differential equation will actually give us the directional cosines. These functions that we find will tell us how to transform from the energy basis back to the position basis. Why is the position basis important? Again, I remind you that it is only in x, y, z, and t, our position space, that we have intuition. So we want to be able to see what these functions look like, the energy eigenfunctions or the momentum eigenfunctions. And it is only in the position space that we have built up this intuition. So we're doing several things all at once. The primary things that we're doing are we've changed our variables to make them simpler. We have extended our algebra by using a combination of x and p and formed a new algebra. And with that new algebra, we then go to the Cartan basis, a dagger a, I, and n. And we then move around and find all the eigenvalues using these raising and lowering operators. And this technique is very similar to ones that we will use over and over again.